introduce today Paul Rosenbaum. Paul is Robert G. Causal Professor Emeritus of Statistics at the Wharton School of the University of Pennsylvania. As we all know, he's one of the guys who have shaped the field of causal inference. Please join me in welcoming him today to our seminar.
So I'd like to talk today about being realistic about unmeasured biases in observational studies. And I hope what I mean by that emerges as we go along. An observational study is a study of treatment effects. One can't run a randomized experiment. Treatment received and outcome exhibited may be associated in an observational study, even if the treatment did nothing to cause an effect. Although we always adjust for observed covariates in observational studies, groups that have been adjusted for observed covariates may nonetheless differ in terms of covariates that were not measured. A better way to say that is that without random assignment, the probability of treatment may depend on relevant covariates that were not measured. That's connecting randomization with the problem with covariates. This is the main source of controversy in real observational studies, and therefore it organizes design and analysis of an observation. The talk has an example, some methods, and some theory for design and analysis. In thinking about unmeasured biases, the context matters. The context is often informing you about the biases that might be present. So the talk uses a simple example, almost a toy example, in which the context is familiar to everybody. Everybody knows that because everybody lives in this world. I'm going to make occasional quick claims about how observational studies should be designed if we want them to be insensitive to unmeasured biases. The proofs of these claims are in my design book, but they're not the focus of this talk. I'm mostly going to be focusing on other things. I'm going to show you some theory that the choice of methods of analysis has a substantial effect on the degree to which the study is sensitive to unmeasured biases. I want to show you also that, perhaps surprisingly, evidence of unmeasured bias may actually make a study insensitive to larger unmeasured biases. So the thing you thought was hurting you might actually be helping you. The example has several control groups, so I'm going to make a couple of comments on that, maybe fewer than are in this remark. The talk is based on this collection of papers. I have several general theses I want to sell you on. One of them is that every observational study is affected by unmeasured biases. But that fact is not debilitating. In other words, the fact that every study is affected by unmeasured biases doesn't necessarily mean that you can't discover a causal effect from a study in which there are unmeasured biases. A prime example would be smoking and lung cancer. Studies were obviously biased in a wide variety of ways. There's no doubt in anybody's mind that smoking causes a lot of lung cancer. It was never a consistent estimate of the effect of smoking on lung cancer, but whatever that effect was, it was big. Unmeasured bias is unmeasured, but it often has detectable consequences. The detectable consequences may either heighten or diminish concern about the ostensible effects caused by the treatment. A sensitivity analysis talks about unmeasured biases, but it's computed from the observed data. So it's a function of the distributions that generated the observed data. If I change the observable distributions by changing the study design, if I change the test statistic, I will affect the sensitivity to unmeasured biases. If we don't have any guidance from statistical theory about that point, we may actually be picking the wrong test statistic, the wrong study design, because somebody in 1942 thought that it was a good idea and he wrote it on the back of an envelope and gave a speech about it, and there wasn't any math and nobody proved anything. But we need theory to tell us when this happens so we know to avoid situations where we're going to be reporting unmeasured biases or an explanation for what we see when in fact it's just poor design or poor analysis. This is the example. So as I said, it's a somewhat toy example, but it has a serious part to it. You often hear it said that a glass of wine each day with dinner prolongs life, perhaps reducing cardiovascular mortality, perhaps by increasing HDL cholesterol levels, good cholesterol. So that's been extensively claimed and studied. A recent position paper by ASCO, the American Society of Clinical Oncology, is sharply critical of this claim. It's pointing first to an increased risk of death from cancer, and then also to increased risks of death from accidents, liver diseases, and violence. Purely as a methodological example, to illustrate methodology, we're going to look at a little corner of this problem. It's the last, not the important corner. The important corner is whether total mortality is increased or reduced by a glass of wine each day, and I don't have anything to contribute there. But we're going to look at the more elementary question, which is whether light daily alcohol consumption increases HDL cholesterol. We're going to use some of the NHANES data. You have access to this data in this particular R package. We're looking at adults aged 20 or more in NHANES 2013 through 2016. So at this time, NHANES and the Centers for Disease Control were saying that binge drinking is 4 or 5 drinks in a day. And it's more or less what it takes to be, quote unquote, legally drunk. Legally drunk is actually a blood alcohol level, but that's about what it takes to be legally drunk. The treated group consumed not binge drinking, but between 1 and 3 alcoholic drinks on most days, meaning at least 260 days in the last year, 5 times 52. They had a median of 520 drinks in the last year. So that's the typical amount a person had in the last year. There are 3 control groups. Control group N is for never. These are people who had fewer than 12 drinks in their life. Okay? They had a median of 0 drinks in the last year. Control group R is for rarely. They had more than 12 drinks in their life, but fewer than 12 drinks in the last year. And there was never a period in their life in which they engaged in binge drinking on most days. They also had a median of 0 drinks per year. The third control group is group B for former binge drinkers. These are people who had a period in their lives when they engaged in binge drinking on most days, but eventually stopped and currently drink, if at all, on at most 1 day a week, 52 days in the last year, and they had a median of 4 drinks in the last year. So I'd ask you to pause and remember that this is a world you know, right? You know these people, right? You met them, they're in your life. You can think of people like each of these people, right? And I want you to think about what else is going on in their life besides what I'm just talking about here, right? A lot is going on in their lives besides that. We have 406 blocks of size 4. Every block contains 1 person from each group. They've been matched for age, sex, and education in 5 categories. This is showing you a bit about what they're like before and after matching. So BE is before matching and EAF is after matching. Taking all of the daily drinkers, right? We match them to never drinkers, rare drinkers, former binge drinkers. You'll notice that before matching, the daily drinkers were mostly men, 2/3 were men. The former binge drinkers were 2/3 or more men, and the 2 groups of light drinkers were mostly women. So we can take that away through matching. After we match, it's 34% in every group is female. The daily binge drinkers were slightly older, but not very much, but that's removed by matching. The daily drinkers, light drinkers, were slightly better educated. They had some college, on average, 2 years of college on average, whereas the average person in the other groups was more like a high school degree. The people we're excluding, they have mostly on average below high school degrees. So these are, again, different people. What is the idea with multiple control groups? So this is the Campbell-Bitterman idea. It's a design element. Campbell and Bitterman said, if there's an unobserved covariate and I can't observe it, maybe I can find control groups that are very different in terms of it. And if I can establish that the outcomes don't depend very much on these very big differences between the control groups, maybe I've invalidated some of the reasons why we might explain a control group difference from a treated group. You'll notice if you've been listening very carefully that we've omitted a lot of people. We omitted all the people who drink twice a week. Those people are out of the study, right? And that turns out to be one of the many things that will increase insensitivity to unmeasured biases, getting rid of people who get milquetoast versions of the treatment. You can do the mathematics out and figure out the optimal number of people who drink twice a week to put in your study, and that optimal number is 0. You don't want any of them. that will increase insensitivity to unmeasured biases under fairly simple models. We're also looking at blocks of size 4 rather than pairs or just two unrelated groups, right? It turns out that that's a better design than pairs or two unrelated groups. Why is that? Suppose I have two people, treated person and a control group person in a matched pair, and the treatment raises the response, raises the HDL cholesterol level. That's what's actually going on. I would expect to see pair differences which have treated people higher than controls. What if there's no treatment effect? And there's just two order statistics, and the selection bias is pushing the people with higher order statistics into the treated group. Then again, I expect to see the treated person in the pair have a higher response than the control, and I expect the two things to look the same. What if I have 1 to 3 match sets? That's different. I expect the one treated person to respond to the treatment and have a higher response, and I expect the 3 control people not to differ systematically. What if there's no treatment effect and there's just selection bias? I expect to see 4 order statistics from the same distribution with an effort to push one of them into the treated group, somebody with a higher order statistic. Now, if you looked at one matched pair, you couldn't see that. One match set block, you couldn't see it. If you looked at 2, you wouldn't see it. But if you design a test statistic that's making an effort to distinguish those two situations, you can actually, in a lot of data, get evidence about whether it's bias or a treatment effect. We'll see how that works in a bit. We have an unaffected outcome. So this is methylmercury. Methylmercury, according to the World Health Organization and the CDC, is mostly, in humans, a consequence of eating fish or shellfish. So there's bacteria in the sea that eat elemental mercury that is from pollution, and they convert it into methylmercury, a bioactive kind, and bigger creatures in the sea eat the bacteria, and bigger creatures eat the creatures who ate the bacteria, and bigger creatures eat the creatures, and that goes on and on and on until at the top of the seafood chain, shark, swordfish, tuna eat those last creatures, and they have accumulated a vast amount of methylmercury. And then the top of the very food chain, you eat the tuna or the shark or the fish, or the swordfish, and that's where most people get their methylmercury. People have looked for methylmercury in alcoholic beverages, haven't found any. It's a little hard to see how you're going to get methylmercury out of something which doesn't have any methylmercury in it. So we're going to take that to be an unaffected outcome. Drinking a glass of wine isn't by itself going to cause you to have an increase in methylmercury. Can we put that to use? So this is what we've been talking about so far. These are daily drinkers, never drinkers, rare drinkers, former binge drinkers. This is their age distribution, looks about the same. This is their education, looks about the same. This is their outcome, the HDL cholesterol levels. They look higher for the daily drinkers than for the other groups. If you do the 6 pairwise comparisons of groups, and make a correction for multiple testing using Holmes' improved procedure over the Bonferroni procedure. What you find is group D is significantly different from the other groups with p-value 10 to the minus 16th, and the 3 control groups do not differ significantly from one another. So what are we seeing? We're seeing that although the N, R, and B groups sound to us to be very different people, they still have the same HDL cholesterol levels, all of which are low compared to the people who are daily drinkers. And we've eliminated chance. Okay, chance is out of the picture for the rest of the talk, right? It's not chance. It's not an accident. Could be bias, but it's not chance. Do you think these people are living similar lives? So I asked you to think about people you knew, right? If I ask one of those people, have you ever tried marijuana? Do you think that would be the same in the groups that had fewer than 12 drinks in their life, or the former binge drinkers? Do you think if I asked, have you ever tried crack, that would be the same in those groups? And so on. So this is looking at the answers to some questions like that. You'll notice again, it's not chance. The p-values are infinitesimal on the right. And you're seeing that 73% of the daily drinkers and 75% of the former binge drinkers have tried marijuana or hashish, and only 9% of the never drinkers have tried hashish. Tell me there's somebody in this room who was surprised by that, right? You knew this, right? Because you knew the context, and since you knew the context, you knew this was going to happen before it happened. Similar things are happening with crack and meth. We're seeing about twice as much methylmercury in the blood of people who are like daily drinkers than in the other groups. And we don't think that's an effect caused by alcohol. We think that's an effect caused by eating more fish. And if you haven't been to the dentist in the past year, the answer seems to be that daily drinkers have been to the dentist much more than former binge drinkers. In all likelihood, it has something to do with people have heard that having a glass of wine is good for your health, going to the dentist is good for your health, eating fish is good for your health, and so they're all in the daily drinking group, right? The binge drinkers haven't heard about going to the dentist, and so they're having a lower rate of that. I failed to mention that the blocks are matched for one more variable. So NHANES doesn't always collect all the data on everybody. It takes a sample of people and collects a little extra data on this and a sample of other people and collects the data on that. So it's a random sample, but there are 200 of our daily drinkers have methylmercury data. So I matched the controls to agree with whether there was a methylmercury measurement. So this is just whether there's a measurement. There's no question about what the measurement is. It's just whether NHANES took the measurement. So on the left, you're seeing what we were looking at before. I merged the three control groups into one, and we're seeing what looks like an effect of alcohol on HDL cholesterol. And on the right, we're seeing the association between methylmercury and alcohol. And there's something troubling about that, which is we don't think that's causal, and the two pictures look the same. Right? So there's a little bit of a problem in sort of believing the left side is a causal effect. The right side is not a causal effect. And we'll think about that some more as we go along. I'm going to present a little basic structure. I'm assuming many of you are familiar with this. I'm going to move sort of quickly through this piece. It's all on the slide if it isn't familiar, so just read it if it isn't familiar. We have treatment, two treatments, Z equal 1 or Z equals 0. It's our daily alcohol consumption. We're thinking about potential outcomes under treatment and under control, of which we observe just one. So we observe the treatment assignment and the observed value of the potential outcome. These may be multivariate, so it might be cholesterol and also methylmercury. We have covariates. The observed covariates are X. The unobserved covariates we're worried about are U. A randomized experiment, a randomized block design might form blocks using a function of the observed covariates. You could use all of them, but maybe you'd use a function of them. And then you determine treatment assignment within each block by a flip of a four-sided coin. Right? The coin is fair and it doesn't depend on the potential outcome. So more precisely, we have this condition, which is ignorable treatment assignment. Ignorable treatment assignment says two things. The probabilities here are never 0 or 1. Everybody's got a chance of getting both treatments. And the potential outcomes don't help you predict who gets the treatment once you have the observed covariates. It's conditional independence of potential outcomes given the observed covariates. If this wonderful condition were true, life would be simple. We wouldn't have to have any real problems in drawing causal inferences. Adjustments for the observed covariates would suffice for causal inference. We often speak of ignorable given something else, maybe a function of X, or maybe given an observed covariate and an unobserved covariate to say we're talking about the right unobserved covariate, though in fact there's only one right unobserved covariate. The guy over here, see my hand. That guy is a familiar guy. He's the propensity score, and we know that if treatment assignment is ignorable, then it's ignorable given the propensity score. The other guy over here also has a name. He's the principal unobserved covariate. So he is the chance of getting the treatment given that you have your observed covariates and the two potential outcomes. He's unobserved. Why? Because we never see the two potential outcomes together, so we can never calculate this. There are two key facts. If this principal unobserved covariate zeta is between 0 and 1, so there's a chance everybody gets the treatment. The first fact is that treatment assignment being ignorable is the same thing as the principal unobserved covariate equaling the propensity score. That's just expression 1 stated in a different way. The second fact is treatment assignment is always ignorable given any function of the observed covariates and the principal unobserved covariate, including the function which throws the observed covariates away. So the whole ball of wax is in the principal unobserved covariate. If you had the principal unobserved covariate, causal inference would be straightforward, but you never have it, so it's not so straightforward. Do notice that the principal unobserved covariate is a function of the observed covariates and the potential outcomes. We're going to build I blocks of J people. We can have 406 blocks of 4 people. There's 1 treated person in each block. We're going to sample observations on the observable quantities, the observed outcome, the observed treatment assignment, and the observed covariates, and assemble them into blocks. We're going to assemble them into blocks so that some function of the observed covariates, you pick your function, is equal for all the people in a block. We are, of course, worried that blocking for a function of the observed covariates hasn't actually controlled the principal unobserved covariate. 2 people might be in the same block, look the same in terms of h of x, but different in terms of the principal unobserved covariate. This can happen in 3 ways. Could be that controlling for h of x doesn't control for the propensity score. Could be that controlling for h of x doesn't control for the principal unobserved covariate because treatment assignment is not ignorable given x. Could be both are true. So what follows is really worrying about all 3 of these problems simultaneously. Let's write F for the potential outcomes and observed covariates for people we're talking about. The principal unobserved covariate is a function of F, right? It's the probability of being treated given F. Let's let calligraphic Z be the set of possible treatment assignments. So we have an ij dimensional vector. Contains 1s or 0s indicating who's treated and who's control. And in every block, we have 1, 1 and j minus 1, 0. Right? So the set Z is a set of a lot of treatment assignments. It's got j to the I treatment assignment. We sample people and blocks to ensure that Z is in calligraphic Z by conditioning on that event. We abbreviate conditioning on Z, vector Z is in calligraphic Z as conditioning on Z. So that's going to make the notation look a little neater. So instead of writing a long thing, I'm going to write a short thing, even though it's a little bit of an abuse of notation. So just to take the simplest case in a randomized block design, the principal unobserved covariate is 1 over j for everybody, right? Everybody has a 1 over j probability of being the treated person in every block. I want to get from that to what we get afterwards. Okay, I want to go from the world where I have just a bunch of people to blocked experiments. So I need a condition on the potential, on the fact that there's 1 treated person in each block. So we haven't conditioned on it. Who is this guy? This is the probability that person ij is treated in block I and the other guys are all controls, right? That's what he is. And I can pull out one of these 1 minus zeta guys and have a product which doesn't depend on who I was talking. So if I now condition on the fact that there's 1 treated person in every block, right? So I'm talking about this probability here, right? Which is in the design, you do 2 seconds worth of stat 1, right? And you see that the conditional probability given this is this ratio, this guy over this guy summed, because this guy is canceling, right? And that's theta ij. He's the residue of the principal unobserved covariate having blocked for h of x. Some of it may have been removed, but there's some left. That's what he is, theta ij. He's important. So that's what I just said in the previous slide. The sensitivity model says what? It says out in the population, people who look the same in terms of h of x have odds of treatment in terms of the principal unobserved covariate that's bounded by gamma and 1 minus gamma. And if you stare at this guy over here, right, you realize what was an odds becomes a prevalence ratio, the ratio of the residues, right? The conditioning has converted it to the ratio of 2 thetas for the same value of I, the same block. 2 people in the same block may differ in their probabilities of being the treated person in that block by at most a factor of gamma. Different statistics, different research designs correctly yield different conclusions about sensitivity to unmeasured biases. So we'd like to understand this so we can make wise choices about how to design observational studies and how to analyze them. I'm first going to do this just by analyzing the data set from the alcohol data. We won't know what that means. We'll see something happen, but we won't know what it means because it's an observational study and who knows what it means, right? On the other hand, we'll strip out the data and put in a normal distribution. We'll strip out the data and put in a logistic distribution or a t distribution. We'll see actually what we see in the data is actually happening independent of the data and is a property of the statistical model. Second, so this is what I just said. So that was very second. We're going to start with a closely related collection of statistics. So some of these guys are old friends. You've seen them before. Some of the guys are they're quite old friends, but they've been around for a long time, even though you haven't really seen them before. And some of the guys are like really strange. Okay. And the interesting thing is the guys who are really strange clobber all your old friends. Okay. They're much better than your old friend. The family is useful because they're all connected. They're all simply related to one another, and yet their performance is very different. So we're testing the hypothesis of no treatment effect. We rank people in each block from 1 to J. So I got 4 people in a block. I rank their HDL cholesterol levels from 1 to 4. The biggest guy gets a 4. The smallest guy gets a 1. Those within block ranks are QIJ. I then look at the dispersion of people in a block. I look at the range of people in a block. I look at the range of the HDL cholesterol levels, biggest versus smallest, not noticing who's treated and who's control. And I find that. I then rank those from 1 to I, and I divide by I to get WI. So WI is the rank of the dispersion within a block. We're going to then take a function of those ranks. It's going to map 0, 1 to 0, 1. And this is our test statistic. So the test statistic says I find the treated person in every block, I get his rank, I multiply him by this weight function, I add it up over all the people. It's a simple test statistic. The family includes things you know, right? A familiar guy in this family says, I don't really want this function kicking around my statistic, I'll just make him 1. And then if it's a paired experiment, this yields the sign test. It's the same test statistic in effect. If instead I take that phi function and I make him the guy who returns whatever I give him, the identity function, right, I would get Wilcoxon's signed rank statistic. So for paired data, this weighted rank statistic is Wilcoxon's signed rank statistic. And if I take any function, I have the general class of signed rank statistics, which have been studied since the 50s. For j greater than 2, taking the function to be 1 all the time gives you the blocked version of Wilcoxon's rank sum test. So I calculate Wilcoxon's rank sum test in the first block, get the rank for the treated person, go to the second block, do the same. I add that up over all the blocks. It's probably the most common thing to do with non-parametric analysis of a block design, and it's in Layman's 1975. If I replace the phi function by the one that gives me Wilcoxon's signed rank test, which is a much better test than the sign test, I get Quade's statistic, who's not necessarily an old friend, but he's certainly been around for a long time. These are the 4 guys we're going to compare, okay? The guy who's got the horizontal line, right, is the sign test or the block Wilcoxon rank sum test. He doesn't care about the ranks of the ranges. This guy here is the guy who just takes the ranks of the ranges and uses them on it, untransformed, and that gives you a Wilcoxon signed rank test or Quade statistic. And then there are these 2 Cobra-like guys who are doing something strange. They're ignoring all the blocks with small ranges and paying a lot of attention to blocks with larger ranges, but they're not letting anybody dominate the whole picture. Right? Nobody gets to run the show, but despite that, they're paying a lot more attention to the blocks with large ranges. If you want some intuition about this, ask me during the question period. Anyway, but there are 4 categories of statistics. Very important set is B gamma. B gamma is a set of these thetas. Remember, the thetas are the treatment assignment probabilities in the blocks, right? What set is it? Well, for a given value of gamma, these are the thetas that are compatible with that value of gamma. These are the treatment assignment probabilities that give you at most a bias of gamma in treatment assignment. So with 406 blocks of size 4, each of these guys is of dimension, each theta is of dimension 1624. They actually live in a flat because they sum to 0 in every block. So the dimension of that flat they all live in is actually 1218. It's a closed and bounded and hence compact set of thetas. The sets are nested. They get bigger as gamma gets bigger. Every set contains the sets that came before. You're assuming less and less as gamma goes to infinity. You pick a theta where everybody has some non-zero chance of treatment or control, and then I can find you a B gamma where gamma is big enough to include that theta. So every possible treatment assignment probabilities are in some B gamma, though it may be a very big B gamma, right? A randomized block design has one theta, namely everybody's probability of treatment is 1 over j, and as a consequence, that theta is in B1, right, for gamma equal to 1, right? There's only one guy in that set, the randomization probabilities. The central problem in an observational study is we have no basis for assuming that theta is in B1, right? And as soon as you assume that gamma is bigger than 1, the problem is not identified. So let's do the sensitivity analysis. How does it work? We're going to reject the null hypothesis when our test statistic is big. This is our test statistic. We looked at it before. It's like a sign rank test. This is the probability that the treatment assignment gives us a particular value of that test statistic. Let's write bracket A as a characteristic function of an event. It's 1 if the event occurs, it's 0 if the event doesn't occur. So rejection means that the test statistic is bigger than t. That's the value we're going to reject. If somebody gave us theta, which they don't, but if somebody gave us theta, we could calculate the probability of this event, right? We would take the probability of each of the possible treatment assignments. We'd work out what the test statistic is in that case, determine if it's bigger than t. We'd sum over all possible treatment assignments, and that would be our p-value. We don't have theta. So we're going to take the worst theta in B gamma. So for gamma equal 1, this is the randomization probability. For gamma bigger than 1, it's the worst in a set of possible thetas. If gamma is really small, it's almost like the randomization p-value. It eventually becomes association is not causation. Any p-value you want is a conceivable p-value. This is doing the sensitivity analysis in the alcohol data. So what are you seeing here? You're looking at the upper bounds on the p-values we were just talking about. The p-value can't be bigger than this if the bias is at most gamma, and we're looking at gamma from 1 to 6 for test statistics. What are you seeing? Well, the randomization test says, no way the null hypothesis is true. The p-value is very small. If gamma is 2, right, again, all of them agree that the p-value is very small. At gamma equal to 3.5, Wilcoxon's test has given up, right? It can now give you a p-value above 0.05. But you notice Quade's statistic and these two guys at the end, the two Cobra-like guys I showed you before, still give you very small p-values. At gamma equal to 4.5, Wilcoxon's statistic is out of the picture, and Quade's statistic is about to give up, but the other two guys are still going strong. At gamma equal to 5.5, U868 has given up, but U878 is still going strong. At gamma equal to 6, U878 is about to give up. So how much sensitivity you report depends a lot on the choice of test statistic. Just to put this in context, Hammond's famous smoking and lung cancer study was sensitive to bias at gamma equal to 6, an enormous bias. The alcohol data is as insensitive as that if you design the study sensibly and you analyze the study with the right test statistic, but choose the wrong test statistic and do a couple of other things wrong, and it will be much more sensitive to bias than that. In particular, all by itself, choosing Wilcoxon's statistic, the most popular statistic for this context, would give you much more sensitivity to bias. I've said a couple of times 1 to 3 is better than 1 to 1. I want to show you a fair comparison of that in the data set. It wouldn't be fair to compare 406 1 to 3 blocks to 406 1 to 1 pairs because there's just more data in 406 1 to 3 blocks. So I need to equate the two. So let's take the simplest model, a Gaussian linear model with additive block effects, additive treatment effects, constant variance, the one you used all your life, and have that be our model. And we're going to calculate the mean of the treated group minus the mean of the control group, right? And that'll be our estimator. If you think about it, M 1-to-1 pairs has variance 2 sigma squared over M. Why 2 sigma squared? Because we're differencing two guys who have variance sigma squared and they're independent, and we're averaging M of them and we're getting an average over M, so it's 2 sigma squared over M. What about 1 to 3 blocks? Well, that's going to have one guy subtracting the average of 3 guys, right? So that's going to give you your 1 plus 1/3 sigma squared, and I'm averaging I of them. If I do that, right, then I can tell you how many 1 to 3 blocks is the same as 1-to-1 pairs, right, by equating the standard error of this estimator. So far as this model is concerned, it doesn't care whether you have I blocks or M pairs. It turns out that 406 pairs is the same as 271 blocks. So that's a fair comparison. Same amount of data, so to speak. Over on the left side here, we're looking at 406 pairs. I picked one control at random from the 3 controls. On the right-hand side, I picked 271 blocks at random. So I'm using all the people in the blocks, right? And I'm just convinced you those two should be equivalent in terms of conventional mean and variance analysis. You notice it's nothing like that in terms of sensitivity to bias. At gamma equal to 3.5, right, Wilcoxon's statistic has given up completely in one-to-one pairs and is still going strong with 1 to 3 blocks. It's about to give up. With gamma equal to 4, U868 has given up over here, but it's still going strong on the right-hand side where we're talking about blocks. So pairs are losing to blocks again. If we come down here to 5.5, U868 is sensitive to bias on the left-hand side with pairs, and it's still pretty insensitive to bias on the right-hand side with blocks. So blocks are better than pairs, right? So, okay, we've killed that example. Right? We've been over that example a lot. How much can you actually learn from one observational study? So let's take the same structure and create a model which generates data, let the sample size go to infinity, and deduce something from the model. That way we'll be sure we know what's happening because we made it happen. We built the whole thing. Things get an I subscript because they refer to a sample size of 5 blocks. This is the model I'm going to use. So the model is your standard block design. You notice that there's an error for a treated response per person, an error for a control response per person. The treated minus control effect is a constant plus the difference of 2 errors, so it's varying from people. And these errors are exchangeable. So if I swap them, I get the same distribution, so the differences are symmetric about tau. I'm going to assume that the treated minus control pair difference has variance 1. So then tau is going to be the effect in units of the standard deviation. So just making an index where I don't have both a mean and a variance moving around and they're canceling each other out. The treated minus control pair difference has variance 1 and tau is its expectation. So I want you to imagine a study that's unaffected by unmeasured biases. There's a treatment effect. There's no unmeasured bias. Treatments are being assigned at random. It's in exactly that case that I want to say the results are insensitive to bias. If I was in this situation, I wouldn't know it. If I tried to convince people that I was in this situation, they wouldn't believe me. The thing I can do in this situation is compute the sensitivity to bias. So it's in this situation I want to find insensitivity to bias. This is called a favorable situation. So this is the case where you would like to report insensitivity to bias. And the question is, will you? We're going to look at 2 quantities, the design sensitivity and the Bahadur efficiency of a sensitivity analysis under a favorable model. So we're going to test no treatment effect when the bias is at most gamma. Fix the power at anything you like, let's say 90% power. We'll pick a sample size, let's say 100 blocks. We'll compute the level of the test that I would have to reject that in order to have that power with that sample size. So maybe it would be a level of 0.1 too liberal with 100 blocks. Maybe it would be 0.01 with 406 blocks. Right? We'd like alpha, this level, to be going to 0 as fast as possible as the sample size increases. Ultimately, the power we pick, 90% power, doesn't matter. You get the same answer for every power. There's typically a number called the design sensitivity, such that as the sample size goes to infinity, alpha is going to 0 if you do the sensitivity analysis with gamma less than the design sensitivity. It's going to 1. Can't reject the null hypothesis, no way, no how, if gamma is bigger than the design sensitivity. So gamma tilde is the limiting sensitivity to unmeasured biases if I had an infinite sample. Suppose I got 2 test statistics and I want to compare them, and they both have gamma below their design sensitivities. So it's a contest now, because one of them is not going to 1 while the other is going to 0. They're both going to 0. You can compute a rate at which the p-value is going to 0, and that rate is called the Bahadur slope. So that level is going to zero exponentially fast, but it may be going at with a better rate with one test statistic than with another. The ratio of two Bahadur slopes is a Bahadur relative efficiency. It can be thought of as a relative value in terms of how much sample size you're getting from one test statistic versus another in the same identical situation. This is better than Pittman efficiency in observational studies. Why? Because Pittman efficiency lets the treatment effect go to zero. But every negligible treatment effect is sensitive to negligible biases. If we missed every single infinitesimal treatment effect in all the observational studies that everybody's ever conducted, it wouldn't matter, right? Who cares about an infinitesimal treatment effect? The Bahadur efficiency is better because it can talk about a treatment effect that's not trivially small. And that's the kind of thing we want to distinguish correctly from unmeasured biases that are also not trivially small. So these are design sensitivities. We're going to look at what happens as the sample size goes to infinity, the number of blocks. This is for a set of normal errors where the treatment effect is half the standard deviation of a pair difference. And what are you seeing here? You're seeing the 4 test statistics across the top. You're seeing match pairs or j equal 2 versus blocks of size 4. And these are the limiting sensitivity bias now for the normal distribution, not for our data. But you notice they exhibit the same pattern as our data, right? This is the same thing you saw in our data. It's happening in the normal distribution. The design sensitivity for 878 in 1 to 4 blocks wins by a mile, right? It's a lot better than Wilcoxon's statistic for matched pairs. If you change the story around a little bit, if you change it to a third, the treatment effect is not a half a standard deviation, it's a third, you see the same pattern of numbers, but they're all a little smaller. If you swap out the normal distribution and put in the longer tailed T distribution on 5 degrees of freedom, you see basically the same thing. If you swap out constant effects and put in half the time I get a 1/3 effect and half the time I get a 2/3 effect, you see the same thing. All of these cases produce essentially this set of numbers, not quite exactly this. So let me show you a couple of Bahadur efficiencies. So we're looking at the relative efficiency of 2 statistics in the same sampling problem. So the top half of this table is comparing U868, the default option in the weighted rank package, to U868 for pairs. The first row is 1. Why? Because I'm comparing the statistic to itself, right? So it's always the same in terms of its relative efficiency. Across the top, we're looking at the sensitivity analysis is performed at gamma equal to 2. The treatment effect is either half a standard deviation of a pair difference or a third of a standard deviation, and the errors are either normal or T5. And what are we seeing? We're seeing that blocks are better than pairs using this reasonably good test statistic. We see an efficiency of 3 in column 3 at block size of 4. Just to pause for a second. Statisticians have worked over statistics for a long time, and a 5% improvement in efficiency is something exciting. This is a 300% improvement in efficiency, okay? So this is something you don't want to miss. The bottom is the double whammy. You're using pairs and you're using the signed rank statistic when you should be using 868 and doing blocks of size 4. In that case, right here, we're seeing a relative efficiency of 24. One observation from that design is worth 24 observations from the other design, okay? Big difference. That is to say, there's a 2,481% increase in efficiency when we're excited about a 5% increase. Again, it's not something we should be ignoring. Okay, so I've tried to convince you that, that the test statistic has a strong effect on the sensitivity to bias, as does the decision to use pairs or blocks. I want to go back to that picture that was troubling us, right? This was the picture of the 200 blocks where the methylmercury was measured. And the picture on the left for HDL cholesterol looks a lot like the picture on the right, which is a little disquieting because we think the left side might be a treatment effect and we think the right side probably isn't a treatment effect, but they look a lot alike. So what should we think about that? So our unaffected outcome, methylmercury, has clearly rejected the hypothesis that treatments are randomly assigned. The treatment assignment is ignorable. You never see this picture on the right if, in fact, there's no effect on methylmercury and if treatments have been randomly assigned. So we've rejected the hypothesis that theta is equal to theta bar, the theta that we would have in a randomized experiment where everybody had the same probability of treatment. I'm going to simplify this story by always using Quaid statistic in a two-sided test with 0.05 level. Actually, you shouldn't do that. But if I started telling you what you should do, it's going to go on. So I'm just going to do one statistic in one way all the time, even though there are better things to do than this. Okay, we have 200 blocks where methylmercury was measured, and we have in those blocks, the HDL cholesterol level becomes sensitive to unmeasured bias at 3.614. So it's exactly at that value you get a p-value of 0.05. Sneeze, and it becomes sensitive to bias, right? So every theta in B3.614 has a p-value that should be below 0.05. I'm sorry, no theta in that set has a p-value above. Everyone rejects it. Right? In parallel, we could do the same analysis to the methylmercury data. It turns out that's actually sensitive at a smaller bias, about 1.99, although the interpretation is different. We've rejected every theta in B1.99. Every one of those thetas has been rejected by this plot, right? And so you can't believe in any of those thetas. But in fact, that doesn't change our sensitivity analysis because our sensitivity analysis is insensitive to all biases that are substantially larger. It's never claimed that they're insensitive to all biases, claimed that they're insensitive to biases in B3614. And so that doesn't change what we said before about sensitivity to bias. Could have, but didn't. On the other hand, there are some elements of B3614, some thetas, right? Some of these 1624 dimensional thetas that are particularly troublesome. Actually, they're now 800 dimensional. In particular, there are values of theta where if I sneeze, I exit B3614, I enter B3615, and at that point, the p-value is above 0.05. There are not very many of those thetas, but there is at least one, right? And there might be a little collection of them, okay? So those are the worrisome thetas, right? I'd like to say, don't worry about them. I'd like to say, actually, I looked at the methylmercury data, and the methylmercury data says don't believe any of them. The methylmercury data isn't compatible with any of them. If that were true, then there would be no gap between the test for bias and the sensitivity analysis. At the moment the sensitivity analysis collapses and can't do anymore, this test for bias is coming in and saying the thetas that are most worrisome to you are not really plausible thetas, right? So we can test every one of the thetas in the troublesome set, which is a small set. And in fact, the test using methylmercury rejects them all with a p-value of 10 to the minus 7. Okay, so none of those guys are plausible. So in this case, there's no gap, right? Every time where the sensitivity analysis has collapsed and can't say anymore, the test for bias has said these biases that you're worried about are not really plausible biases. So the evidence of bias in methylmercury has strengthened rather than weakened the claim that there's actually a causal effect on HDL cholesterol. We can carry this a step further. We could test every theta, right? There's a set of thetas, we could test every one of them. And in the process, we could reject some of them and accept others, right? So let's do that. Let's take all the values of theta that we do not reject and put them in a set, cap theta. So cap theta is a funny guy. He's a confidence set. If we test at the 0.05 level, he's a 95% confidence set. Because when I test the true value, the chance that I reject it is only 5%. So it covers the true value of theta with probability 95%. That's, basic definition of the confidence. It's a strange set because it doesn't collapse to a point the way we're used to as the sample size goes to infinity. In fact, his dimension gets bigger as the sample size gets bigger. So he's not going to be telling us the last word on what theta is. So what is a sensitivity analysis that is informed by the test? Instead of letting theta be anywhere in B gamma, we're going to restrict it to the confidence set. So you have to have passed the test, the methylmercury test, in order to be considered as a possible biased treatment assignment. So that's a smaller set. So if I maximize the p-value over a smaller set, right? I'm going to get a smaller maximum or a smaller p-value. It will be less sensitive to unmeasured bias. So we're comparing the uninformed sensitivity analysis, the worst theta in B gamma, to the informed sensitivity analysis, the worst theta in B gamma intersect the confidence set. We always have a p-value that's never larger than we saw before, but sometimes we actually see one that's genuinely smaller. In particular, P 3.614, the guy we've been talking about all along, he's 0.05. But if I confine theta to the confidence set, the minimum p-value occurs at 3.82. Okay, I get a p-value of 0.05 at 3.82, a bigger value of gamma. Some of you will have seen an amplification. The amplification, if you've seen it before, is just saying that's not a trivial reduction in sensitivity to bias. It sounds a bit trivial because it was so insensitive to bias to begin with. 3.6 to 3.8 doesn't sound like a giant deal. But if you were down at 1.3, 0.2 would seem pretty good to you, right? So just let me summarize what we've been saying here, right? We've been looking at this picture. It becomes sensitive to bias at 3.614. This picture is forcing us to believe the bias is at least about 2. But it's not forcing us up to 3.614. The smallest bias that can explain both pictures, there's only one treatment assignment here, so the smallest bias that can explain both pictures is 3.82, bigger than the bias that can explain on the left. Therefore, the conclusion is more insensitive to bias than before. So let me summarize. Unmeasured biases, I've claimed, are present in every observational study, but they may not be debilitating. We need to be able to reason in the presence of unmeasured biases, but that doesn't mean that we can't reach causal conclusion in their presence. Statistical theory can aid us in avoiding mistakes that exaggerate sensitivity to unmeasured biases, right? And we've seen a couple of ways that can happen: the choice of test statistic, the use of multiple controls, avoidance of having people who get slight doses of treatment and trying to make some effective use of them. A variety of things affect the sensitivity to unmeasured bias. We can measure these things in terms of either design sensitivity or Bahadur efficiency. Design sensitivity is a coarse measure. It's sort of telling you the limiting sensitivity to bias. Bahadur efficiency is saying what's going to happen when you're actually working below the design sensitivity, which test statistic would be better. Evidence of bias treatment assignment may actually increase insensitivity to unmeasured bias, as we saw with the methylmercury example. And so I didn't say too much about two control groups, but there's actually a formalization of what those multiple control groups are doing to strengthen the formal conclusions. So let me close there, and I'd be delighted to have your comments and questions.
We have two discussants.
I'm sorry. Yes.
One of them is me, the other one is Melody Huang. So maybe we'll provide some comments and then we can collect questions from the audience. Would that be okay? Great. Over the decades, Paul has not only written these excellent papers, these great songs, but altogether they constitute a cohesive theory of causal inference in observational studies, where some salient elements are that the observational study is to be carefully designed to approximate a randomized experiment. Paul has taken very seriously this principle from Cochrane, Dorn, and others, which we adopt today in statistics and epidemiology and in other fields. In his theory, the randomized experiment is a particular case of an observational study via his sensitivity model by the index parameter gamma. So in a very transparent and elegant way, we can connect these two fundamental settings for science. Importantly, Paul has chosen to use matching as his vehicle for adjustment in such a way to adjust for covariates and provide a data structure, an adjusted data structure that self-analyzes, in the sense that evidence is kind of like evident. The study almost kind of like speaks for itself. We saw this today in his figures. So after matching, Paul likes showing plots. And I think that's very powerful when it comes to speaking to policy experts, to medical doctors, to scientists. And Paul has done this in a very deliberate way. Fourth, sure, Paul is a statistician. He gets it. Statistical efficiency, it's important. But in this phase of bias, of this inherent ambiguity of an observational study, Paul has placed more attention to carefully thinking about bias than being as efficient as one can be, which is important, sure. But bias is the main consideration. And to me, this is something very interesting. We were discussing this with Jamie a year ago over dinner. It's interesting to observe the subjects on which Paul has chosen to write and not to write, the trends he has chosen not to follow. Over the years, he has kind of like maintained this line, which again, now we can see that constitutes this cohesive theory of observational studies. He has focused on transparency, methods that are grounded on statistical theory, classical statistical theory, as we saw today. Many of these things, I think, are kind of forgotten. Today in the reading group, we were talking about the importance of the selection of the test statistic. Something very important in classical statistics, but now in causal inference, this idea seems to be forgotten in many settings. How critical is the choice of the test statistic? In such a way that we can do better science. So this idea of statistics being the interface between mathematics and science. Paul has been right there, okay? And I think it's important for statistics to do that. Not just mathematics, not just algorithms, both of them. Well, these inventions, the propensity score we've done, optimal matching, randomization inference, sensitivity analysis, evidence factors, and all of them are present in today's work. We saw the propensity score integrated in this idea of the principal and observed covariates, optimal matching by forming balanced groups, balanced blocks of size 4, the importance of the test statistics again, the sensitivity analysis, this time guided by a negative control outcome, and evidence factors by having these match groups, the treated group matched to 3 controls. Okay, so we saw that. And now I'd like to provide some more specific comments into a specific aspect of the work that Paul showed today, and hopefully offer an extension. Today we saw optimization in 2 stages. In the design stage, by solving this optimal matching problem that minimizes covariate distances to form the match groups, the blocks. That's a very interesting problem in itself, but I want to discuss the second one, which is this optimization approach in the analysis stage, where Paul is solving a generic problem of this form. More specifically, he's going to compute, he's going to find the value of gamma, for which he barely rejects the null hypothesis of no treatment effect, constrained, disciplined by the behavior of the test on the negative control. That's the general idea. And what I want to emphasize is that this boils down to a very concrete mathematical program. And I love when these things happen, they appear. When there's the data, there's the optimization approach, and I can see how we're acting on the individual level data in connection to a randomized experiment. And this emerges very, very clearly in Paul's work today. Concretely, he's minimizing this quadratically constrained quadratic program, quadratic in 2 senses, because we have a quadratic objective function and quadratic constraints. What is the idea? The idea is that this problem here is indexed by this parameter gamma. For different gamma, we're going to compute the thetas, the probabilities of assignments within groups, the worst case ones. And these worst case probabilities of treatment assignment, now they're constrained or disciplined by this first constraint on the negative control outcome. This is where the surprising result comes from. Okay. Because we're not seeing the negative control behave as a negative control, nonetheless, that is helping, because he has very close traction on the unit level data. Something that to me is interesting about this sensitivity analysis is that he's kind of like using the structure of the actual data. It's a sensitivity analysis that uses that in a way that I find that it has more traction than other sensitivity analysis models. But I may be wrong. That's one of my questions, actually, for the end. And from here, this is so clean and crisp that we can see that we can do more things. For example, it is very easy to add a second test for bias for a second negative control outcome. It's just going to be another constraint. Also, we can connect this to other works by Paul, Colin, and Dylan, where if you have two outcomes, but one treatment assignment, the worst case bias can only screw you up so much in one direction, but that constrains the bias for the other outcome. This would just be another constraint here too. Very easy to accommodate. And what is very interesting to me, and I wonder if Paul left money over the table here, is that from the theta ij's, he can compute the worst case principal and observed covariates. My question is, can we do something with that? Because if we had this to begin, I don't know, they could have informed the analysis a lot, the matching in some way. They're the worst case ones. We have discussed this briefly. I'm sure Paul will come up with something, if there is something here. And as a possible extension, so Paul solved the problem very much in the spirit of observational studies, of this tradition. There are other traditions in observational studies of separating the design and the analysis stage. He solved the matching problem, conditioning on the match design. He did the sensitivity analysis. An alternative is to do this in one go. So, subject to a match design D now, which is indexed by forming the match blocks M, constraining the distances, and even achieving a level of covariate balance. Okay, so you are finding a match at the same time that you optimize for the behavior of the test statistic for the primary outcome, subject again informed by a test on the negative control. So I wonder if this is a possible extension. And a few general questions. If time permits and we have questions to time to discuss this more broadly, these are more general questions. If time permits, I wonder if we could discuss this with Paul on the role of the sharp null hypothesis. My understanding is this has been central in today's presentation. You have worked on extensions of the sharp null hypothesis, say, to attributable effects, dilated effects, also the weak null. You have worked on all this, and I was wondering if you could tell us more about how this sharp null hypothesis falls in this more general framework. If we have time, I was wondering if we could discuss this. Also, this idea of conditioning. In matching, the way we're conditioning, we're adjusting for covariates is very clear, right? And I was wondering how the way matching is conditioning is fundamentally different to the way regression conditions. Because regression is also solving a weighting problem, an equivalent weighting problem. There is a form of conditioning. I wonder what's the connection between these forms of conditioning or differences. And then sensitivity analysis, which are really important in our understanding of robustness of findings. If we could speak about how your sensitivity analysis model differs from other sensitivity analysis models. These are very big questions, kind of like open-ended questions, perhaps ill-posed questions, but I was wondering if it would be interesting to discuss them more. I have to thank my funders. Thank you for listening.
Hi everyone, my name is Melody. I'm currently a postdoc here at Harvard, and I'm very excited to be here. It's an honor to be discussing this great work, which I think has been foundational in all of our research. And so I'm going to provide, I think, a high-level discussion of two of the topics that we touched upon, in particular sensitivity analysis and design sensitivity. So hopefully minimal math, since it's the end of the day. Okay, so everyone in this room knows, but causal inference relies on strong underlying identifying assumptions. And so the challenge here is that the credibility of our causal estimates depend directly on the plausibility of the identifying assumptions being true. And so as an example of a common identifying assumption that's used in practice, especially in the context of observational studies, we tend to leverage something known as selection on observables, where we basically say that given a set of pre-treatment covariates, any sort of confounding effect we get from selection into the treatment is ignorable. So this tends to be up for debate. Oftentimes in applied work, right, it's hard to say whether or not we fully accounted for all of the covariates for this assumption to be true. And so one approach to evaluating robustness to these untenable assumptions is the use of sensitivity analysis, which I think Paul has really pioneered in our field. And so to quote P. Ernaud and Frédéric Sauvier on the importance of sensitivity analysis, they basically say sensitivity analyses can educate debates because scientists can agree on their validity without reaching full agreement over what constitutes plausible causal knowledge. And so essentially, when thinking about at least the selection on observable assumption, sensitivity analyses allow researchers to quantify how strong a confounder has to be before their research conclusions are overturned. So I'm going to focus on selection on observables and when we can apply sensitivity analyses to other identifying assumptions. Okay, so I'm going to provide a very quick summary. So if we recall from the talk, we have this theta parameter, which indexes I over the blocks and then J for each individual within the block. And basically, it's going to be equal to this probability, which is proportional to this odds ratio of the principal unobserved covariance. And so basically, if we think about each theta ij within each block, we can take the ratio of theta ij over theta ij prime. And so if this unobserved confounding assumption holds, then we would expect that within each block, because we've blocked on the covariance, there should be no difference between these thetas, right? And so if there is unobserved confounding, then we can basically constrain the differences in these ratios by 1 over gamma to gamma. And so at gamma equals 1, again, then we basically have no unobserved confounding. We can increase gamma and basically compute our test statistics to allow for more and more unobserved confounding. So I want to note really quick, this style of sensitivity analysis has been informally referred to as like a Rosenbaum style sensitivity approach, right? So this has become common in the literature. So in the last few decades, I think there have been different sensitivity analyses that have been introduced for a variety of different estimation approaches. And so now we have lots of different ways to think about sensitivity analyses for matching, outcome modeling, and weighting. They all generally follow a similar structure. So very informally, the structure tends to be, we first think about the quantity that we're able to estimate using our observed data. Here I've represented that with 5x. And then we think about the quantity we would have estimated if we could observe all of the confounders that are necessary for our assumption to hold. So I'm going to note that as phi star of x and u. So once we have these two quantities, what we can then do is we can define an uncertainty set that essentially constrains how different this thing that we can't estimate with this oracle quantity that we can't estimate. And so how we define this uncertainty set and how we constrain the differences between these two quantities is going to dictate sort of the structure of our sensitivity model. So on the previous slide, we saw that constraining that theta term, the ratio of thetas between 1 over gamma to gamma, that's one way to think about basically the differences between these two quantities. We can basically change that distance metric to suit whatever context we're in. So once we have this uncertainty set, we can then optimize over it to find the worst case value of a test statistic. Right? And what we're going to do is we're going to repeat this with increasingly larger and larger uncertainty sets until we end up with a null result. Okay, so I think a natural question that comes up is, which I think Jose touched upon, is we now have a lot of different ways to think about sensitivity analyses and a lot of different ways to construct these uncertainty sets. So are there features of a sensitivity approach that one might prefer when conducting their analysis? Okay, and so we have our sensitivity analyses, and then now I want to talk about design sensitivity. So in general, I think sensitivity analyses are valuable ways for us to think about how reliable our results are in the presence of omitted confounders. But the drawback is these are oftentimes conducted as post hoc secondary analyses. And so if we find that our estimated result is easily overturned by a relatively weak confounder, we kind of hope for the best and just bury it at the end of our paper, right, which is not very promising. And oftentimes we want to return back to the analysis and alter our estimation approach, try to like hike up this alleged robustness. We might end up introducing bias into the analysis. And this practice violates something we call the design principle, which forbids consultation of in-sample outcomes when selecting an estimation approach. And so I think this idea of design sensitivity essentially leverages the theoretical results we have from sensitivity analysis to help us understand how to improve robustness to unobserved confounding at the design stage. And so related ideas to design sensitivity are the power of a sensitivity analysis, as well as this idea of relative Bahadur efficiency. But these are all targeting, I think, the same idea, which is how do we change our design choices so that we're more robust to unobserved confounding? So I kind of think of this as essentially moving the goalpost. So this whole framework allows us to consider when there's a greater degree of robustness to unobserved confounding from changing something in our design. So sometimes these changes are a matter of changing our estimation choice. So as an example from the talk, we might want to choose to block 1 to 3 ratios of treated to control units to help distinguish selection bias instead of matching pairwise. Other times, these can have more consequences, right? They might involve changing our test statistic altogether or omitting diluted versions of the treatment. So I think of it as moving the goalpost in the sense that maybe with our original estimate of interest, our original test statistics that we were interested in computing, we can't actually estimate these things without being extremely sensitive to omitted variable bias. But if we're willing to move the goalpost and estimate a different quantity, we can at least be more confident in the credibility of our estimate, right? And this basically provides us with a way to think about how we navigate those trade-offs. Okay, so I want to end with some final questions. The first is, I wanted to hear your thoughts on how we think about integrating ideas like design sensitivity into applied researchers' toolboxes, right? So in an experiment, we tend to pre-register, but that hasn't been common practice, I guess, in observational studies yet. Do we see that basically, do we think that basically we should be pre-registering for observational studies, and if so, how does design sensitivity fit into that? My second question is, how do you see the notion of design sensitivity and Bahadur efficiency being generalized to alternative estimation approaches in observational studies? So things like regression or weighting, or even beyond this selection on observables assumption, can we think about leveraging this sort of idea for other designs in observational settings? And then my final question is that in cases where it's less clear-cut which design strategy results in a better design sensitivity, so sometimes we see that it depends on the DGP that we've chosen, or it might vary depending on the context. How should researchers actually choose their estimation approach? So how do they decide if there's any sort of disagreement? All right, thank you so much.
So let me thank both Melody and Jose for very generous comments, maybe slightly over the top comments, but nonetheless, very nice comments. I want to pick up on 2 things. One from Melody's talk, one from Jose's talk. So I'm not great at spontaneously coming up with something new, so I'm going to tell you about 2 of the most beautiful theorems in statistics. Well, they're not my theorems, but they're 2 of the greatest, and they have relevance to this. So one of them is about the question of the sharp null, right? So the sharp null says, the theorem I want to tell you about is due to some people you've probably heard of, including Lehman, Fraser, Chaffee, and Stein. So this is the theorem which doesn't sound at first like it has much to do with this, but we'll come back to it. They say, let's stick with I blocks. We have I blocks, J people in each block, just as we had in the talk, and they consider a null hypothesis, a non-parametric null hypothesis. So in block I, there's a continuous distribution, which depends on I. Go from one block to the next, the continuous distribution is the same. And if you get the treatment, you get an outcome from this distribution. And if you get the control, you get an outcome from this distribution. Okay. So I would like you to imagine going to Congress and trying to convince them to fund a $1 billion program to make sure you get the treatment rather than the control, given that your response is going to come from this distribution regardless, right? So that's their null hypothesis. Their null hypothesis says that go from block to block, you get different distributions. Block 1 maybe has a normal distribution, mean 0 and variance 1. Block 2 has a normal distribution with mean 2 and variance 7 and so forth, but it's always the same for everybody in the same block. So I want to test the null hypothesis, right, that's true. That's the null hypothesis. And certainly in a certain sense, if that's the true situation in the world, there's no treatment effect. It's not quite this hypothesis, right? It's a slightly different hypothesis, but it sounds like it's a reasonably convincing version. The theorem, which you would find in Layman's chapter 5 in his testing book, says there's only one test for this problem. One test, that's it. It's like the old guys did these things, right? They did these wonderful things where they told you, we finished this area of the subject. It's all done, right? And so that's what that hypothesis, that theorem says. And the one test there is for this hypothesis is Fisher's randomization test. It's the only test which has level alpha for every possible choice of these distributions. So that's a very general kind of null hypothesis, and there's only one way to test it. What's beautiful about the theorem is it uses the complete sufficiency of the order statistics to prove this. So it's easy to pull a rabbit out of a hat if you put a rabbit in the hat at the beginning, right? But this is a promise that there ain't no rabbit in this hat no matter what you fool around with, right? It's a very hard kind of a theorem to prove. What the theorem says is essentially you need to, because of complete sufficiency, the test indicator function has to be right for every set of order statistics. And because the order statistics are sufficient for these guys, complete sufficient statistics, the only way you can do that is by permuting the order statistics. Permutation tests are the only tests that have this property. So what does that have to do with this? Well, one thing it has to do with, it seems to suggest that what was Fisher's randomization test of this guy is actually identical to a test over here, which seems very different from it, right? It's in fact true that this can be true while this is false, but you'll never know, right? There's no way to know that it is true. So for example, it could be that the treated response for a block is a normal distribution with mean 0 and variance sigma squared. The control response is a normal distribution with mean 0 and variance sigma squared. And they have some correlation rho. If rho is not 1, right, this hypothesis is false because the treated guy and the control guy are different, right? So, but this hypothesis is true, right? And yet the only way to test this family of hypotheses is to test what we thought was really dependent on this. And the reason is we can never see RT and RC jointly. The correlation actually is irrelevant as a consequence. The same test is necessary for testing this hypothesis as this. So this is one of the reasons, my love of this theorem, okay, that I don't actually worry too much about Fisher-Sharp null hypothesis. It's giving you exactly the same test as this alternative hypothesis. This hypothesis gives you the same exact Fisher randomization test, and there's just no way you'll ever convince anybody to use the treatment if this null hypothesis is true. You can sort of say it a different way, which is kind of if you were thinking algebraically about it, right? This hypothesis is kind of like the factor group, right? This is like the group, and that's the factor group. The stuff that's in that was lumped together to make the cosets doesn't really matter, right? The thing that was lumped together to get this distribution, when this is not true, doesn't really matter. Right? Anyway, that was one of my two most beautiful theorems in statistics. Again, I had nothing to do with this wonderful theorem, but it is a nice one. I would definitely recommend it for a Sunday afternoon when you have nothing to do and you have an hour and you want to see it. It's really a pretty theorem. It's really a source of enjoyment to read it. The other candidate I have for the most beautiful theorem in statistics is the Burke-Jones theorem. This is by far the most beautiful theorem that nobody's ever heard of. Okay. And it's directed at Melanie's question of what would I do if I had to choose a test statistic in ignorance of what the best test statistic would be, given that I look at that table and I see it really matters a lot and I don't know which one to choose. The Burke-Jones statistic says I have two tests, T1 and T2, and they each have a Bahadur efficiency. Okay. I get a p-value from T1 and I get a p-value from T2. We have this rule about not peaking, but we're going to peak. Okay. We're actually going to look at the smaller of the two p-values. Okay. And the Burke-Jones statistic theorem is about that. It says I'm computing, say, two columns of that matrix that I gave you, two columns of different test statistics applied to the same data, and I want to use the better one, the one that gave me the smaller p-value. Right? It sounds like an awful thing to do. It sounds like, that's what you get, you flunk stat one for doing, right? The Burke-Jones theorem says there exists a test with the better Bahadur efficiency of these two tests in every situation. So it's not a promise about the best test ever in the world, but it's a promise that you're always going to get the better of T1 and T2 every time you do it in terms of Bahadur efficiency. And they almost do it wrong, right? They almost do the stat one error and take the minimum p-value and pretend that's a p-value, right? But they say, no, we won't do that. We'll take that guy, call him P star. And he's not a p-value. He's small too often to be a p-value. But he is a statistic. I can compute him from data. It's the easiest thing in the world to compute him from data. I run the two tests, I get the two p-values, I got P star. Then there's a little bit more work. So I work out the null distribution of P star. That's no longer, it's not a p-value, but it is a statistic. I can get a p-value from it if I can work out the null distribution. The theorem says if I compute the p-value from this guy correctly using its true distribution, I get the Bahadur efficiency of the better test in every possible situation. And it isn't actually confined to having two tests. You can have 10 tests. You can have 50 tests. You can have infinitely many tests. You can have uncountably infinitely many tests. It's an amazing theorem. Why has nobody ever heard of this theorem? Well, for one thing, it was published in the Scandinavian Journal. Okay, so that didn't help. And the second thing is they weren't kind in, they never presented an example. Okay, I don't mean they didn't present a data example. I mean, they never actually computed the distribution of P stars. So, the thing that seemed like it's a lot of work wasn't there, right? And so it seemed like maybe this was kind of a scholarly piece, right? But actually, you can do exactly this, and it works like a dream. So you can actually compute the better of the two test statistics, work out its null distribution. You're actually working out. You can, in some cases, you can get the exact distribution, but you can always approximate it using a normal approximation to the distributions of the test statistics. Got to be a little careful when you do normal approximations with Bahadur efficiency because you got to do it in the right order. You get the wrong answer. But nonetheless, you can do that, and you can do that in sensitivity analyses and observational studies. So you could actually go through the 4 columns of that table and pick the smallest p-value in each case and make a correction for multiple testing. And it's almost like you didn't make any corrections at all. Why is that true? It's true because if I have Bahadur efficiency and they're different, one of these p-values is heading to 0 exponentially faster than the other. And now I'm going to correct for multiple testing. What's the chance that the guy who's heading to 0 exponentially faster than the other is going to lose? 0, right? I mean, that's declining at a magnificently fast rate. And as a consequence, the correction for multiple testing is almost nothing. It's almost always the case that if you go out far enough, the test statistic with the better Bahadur efficiency has got the smaller p-value, and there was no multiple testing problem to begin with. Takes a little bit of work to do convince yourself that that's true. A little bit more work to get the distribution of P star, but you can do this. It's actually not difficult to do. And if you, instead of using this is a weighted rank package in R. If you do this thing, you'll get the table I showed you. If you do this function, you'll get the Burke-Jones theorem applied to it, and you'll get the corrected smallest p-value for multiple testing. And what it's doing is it's working out the joint limiting distribution of this guy, these joint multivariate normal. They usually have enormously high correlation. Why? Because it's the same kind of test statistic computed from the same data. How different could they be, right? So they're very highly correlated, and the correction for multiple testing is very small. YTT, testing twice. So I'm happy to chat about other things.
5 minutes passed, but I want to allow someone else to ask questions.
All right, so I had the same question as Melody. So I think this answer is basically you telling the applied people like, hey, don't worry about it, just do everything and then apply this, right? But I was curious still from a pedagogical point of view, because the phenomenon that you found was actually extremely surprising. The fact that, in my opinion, again, like the fact that the gamma parameter is actually a function of the test statistic as opposed to just the sign mechanism. But could you at least like say some, maybe like intuition of why the two magic test statistics, I forgot what name you gave it, was doing better than the rank one?
Sure.
Just so like pedagogically, like, you know, for a practitioner, they might want to know which test statistic to even like use.
Sure. So let me. So I treated mine as controlled pair difference. I'm just going to do the paired case. Okay. So I have a match pair difference. There's a function called the ABZ function. Which is the probability that the match pair difference is positive, conditional on its absolute value. So if I condition on its absolute value, there's two things that can happen. It can be positive or negative. This function is called ABZ because it's for Albers, Bickel, and Zwett. It was used in a paper they wrote to expand the behavior of general signed rank statistics. And this essentially tells you everything you need to know about a signed rank statistic. So this is what the Albers, Bickel, and Van Zwett thing looks like. So on this axis, we're going to have the function, right? And on this axis, we have the absolute pair difference, right? And what you see, this axis goes from 0 to 1 because it's the probability that the sign is positive, right? If you have a normal distribution, it sort of does this, right? As the absolute value increases, the probability is going to 1. If you do a logistic distribution, it approaches an asymptote, but it's not 1. If you do the double exponential distribution, it approaches an asymptote, which is not 1. If you do the Cauchy distribution, it does that, okay? So what is that telling you? The normal distribution, God lives in the tail, right? And God is in the tail of the normal distribution. The further out in the normal distribution, the more you learn about truth, right? Which is very incredible, right? I mean, it doesn't really sound plausible. It's a problem with the normal distribution. For the double exponential and for the logistic distribution, it's approaching an asymptote. It's saying what? If the absolute value is larger, right? You're learning more, but there's a limit to how much you learn from one observation, right? Which sounds more plausible than what we see for the normal distribution. And for the Cauchy, it's saying, if you go out far enough in the tails of the Cauchy distribution, you're not learning anything, right? Only in the shoulders of the distribution, where it's not zero, but it's also not out in the tails, are you learning. It turns out that the value of gamma corresponds with a horizontal line in this picture, okay? What is gamma doing? It's taking whatever absolute value you saw and saying the chance that it's positive enters value of gamma over 1 plus gamma, right? So a value of gamma over 1 plus gamma is the probability that the pair difference will be forced to be positive by selection bias, not by a treatment effect. So it corresponds to a horizontal line. It's always gamma over 1 plus gamma. The guys down here, right, they're killing you. They can't get up to what the sensitivity analysis will do. The guys up here are helping you. They're positive too often to be explained by a bias of size gamma. So suppose this is 3 for the normal distribution, right? If you could get millions of observations at absolute value of 3, right, you would be insensitive to very, very large biases from the normal in this case, because it's close to the asymptote. It's probably closer to 5 to the asymptote. You'd be, okay. So essentially what's that telling you? You want to weight these observations high. Remember my picture with the functions that were ignoring the small absolute differences? They're getting rid of these guys who have no chance of being insensitive to a bias of gamma and keeping these guys who have a chance. Why do we need to do things like the Burke-Jones theorem? Because if you are upweighting these guys and you got a Cauchy distribution, you're probably doing the wrong thing. You should be upweighting the middle, not upweighting the extreme tail.
Let's thank very much Paul once again.